Joining us for this third video in this chapter. This is where really for the first time we're going to actually start talking about sort of sibling rivalry among different reactions that share a common intermediate. So we're going to be talking about the competition between E1 reaction and the SN1 reaction because they come from the exact same carbocation intermediate, and you'll see that sort of rivalry bit here. And just to introduce to you like what a E1 reaction is, first of all, I should say that we we talked about this exact same reaction earlier in the context of SN1 reaction, so you might be surprised to see the exact same setup here, and that's because we didn't tell the exact whole story earlier, and so it was not a lie that we do get this SN1 product, but you actually would get, if you do this reaction, this setup, T-butyl bromide, or this T-butyl bromide. By the way, if I haven't mentioned it yet, this group can be abbreviated as T-butyl. The T-butyl bromide can be placed in water to see the SN1 product as well as this E1 alkene product. Okay. And they're kind of in competition with each other because they come from the exact same carbocation intermediate. Just to sort of review for SN1, right? The solvent can sort of sequester or attack as a nucleophile this very electrophilic carbocation intermediate to give us the product. Whoops. And maybe another water molecule could pick up the extra proton, which will give us the SN1 product. Another equally possible scenario is that the water, remember, is not a strong nucleophile. It's also not a strong base either at all, but it can act as a base to pick up a proton. We just saw that here, and because of that, it's also equally possible that the water picks up a proton, H plus, to quench this carbocation so that it's neutral. Okay, now this would be an E1 product. And notice we both ended up with hydronium ion. But so that's the E1 reaction or E1 product, which stands for elimination unimolecular. And then you might wonder, it's really important for you to know what this 1 stands for. It stands for unimolecular, meaning, right, in the rate determining step, there's only 1 molecule involved. Here's a step where 2 molecules are involved, so I hope it makes sense to you. This is not your rate determining step. This is the high energy species, and getting to that is the hardest part. So this is the rate determining step, and you notice there's only 1 molecule involved, right? So that's why SN1 and E1 are really siblings. Right, they come from the same intermediate, and if you have siblings growing up, you might relate to this very much. SN1 and E1 are always in competition. Oops. As in, both of these are equally possible always, but let's think about factors that might favor E1 over SN1. Okay, one of those would be temperature. Why is that? Well, let's think about the very fundamental Gibbs free energy equation. Part of the reason is this really explains everything that ever happens in this universe, right? And so it's obviously very important to think about. And when you dissect this equation, remember, the more negative delta G is, the more likely that phenomenon will happen, or in this case, that particular reaction pathway will happen. We notice that there's a T term here, right? That means that if the temperature is elevated, the entropy factor becomes important. Because mathematically it's multiplied by the temperature. So if the delta S is big, as in if delta L is largely positive, that's going to make delta G very negative, right? Negative temperature times delta S. So the entropy factor becomes important. So let's think about the entropy factor for these reactions. When you mix these two and E1 happens, right, you're going to get the eliminated product of the alkene. The water that try to react with this, it's still a separate entity, not part of the molecule. And then of course bromide is sort of left as a leaving group. Okay. So what am I saying? We went from 2 molecules or 2 particles to 3 particles in the end. What does that tell us? If you have more particles, that's more chaos, more disorder. So can you guess the delta S sign for this reaction? It's positive. The entropy increased, right? Delta S is positive, is in other words, because more particles. Now, when the SN1 reaction happens, right, the water molecule really splits into OH and the proton, and really we only get these 2 particles. In other words, delta S is largely remaining the same. So delta S is pretty much 0, right? Like the entropy didn't increase because you went from 2 particles to 2 particles. So what does that tell us? Well, that means that when temperature is elevated, E1 is favored. Okay. Conversely, when the reaction temperature is low, elimination is not as favored. Now, that doesn't mean SN1 is definitely favored. It's just that E1 won't be as favored. So likely, it's going to go through an SN1 reaction at lower temperature. Okay. Now, let's think about the another factor, and that would be the nucleophilicity of the solvent. If the solvent has almost 0 nucleophilicity, then E1 would be favored, and that's pretty easy to understand, I think, because SN1 is a nucleophile. By definition, it's a nucleophilic substitution. And here's a good example of that. Let's say we have this alcohol substrate, and we treat this with concentrated sulfuric acid. I don't know if you knew this from Gen Chem or not. Concentrated sulfuric acid is basically 100% sulfuric acid. We would call that a neat liquid because it's not diluted as a solution. It's just 100% of some substance without being dissolved in something as a solution. Okay, so it's a neat sulfuric acid liquid, liquid, and that tends to encourage E1 reaction almost exclusively. Why is that? Well, let's think about the mechanism. Right, this sulfuric acid, of course, looks like that, and it's one of the strongest acids there is, meaning that it would like to protonate it out. Anything and just about anything that has either a lone pair or a pi bond, it would be protonated by sulfuric acid. And of course, alcohol has a lone pair, so it would be protonated to become oxonium ion like this, which is now, of course, a very good leaving group, because when it leaves, it's a stable water molecule. Maybe we'll say that's a good leaving group. That leaves, of course, this carbocation. Now, at this point, what are the potential nucleophiles? Well, one of the potential nucleophiles would be the water that left, because water is weakly nucleophilic, remember, and that definitely can do SN1 reaction, and it would. So sometimes this actually does come back and attack this carbocation, but you notice if that happens, you just go back to the study material. So nothing really happens, nothing productive, that is. Another thing that potentially could be nucleophilic might be the conjugate base of this acid, which of course looks like that. But remember, nucleophilicity goes along with the basicity of the structure. And remember, sulfuric acid is a super strong acid, meaning that the conjugate base is not basic at all, which means this is really not nucleophilic at all, not even a little bit. Meaning this cannot really attack this carbocation. Okay, so what path is left? Well, the only thing that's left is an E1 reaction, and so one of the things that what's going to happen is this proton would water would grab this proton next to the carbocation so that you can form this E1 product. Okay. Now, if you're pretty sharp, like you might have wondered at this point, gee, how come water wouldn't grab this proton next to the carbocation to form that alkene? Right, let's think about that. Why this would be the major E1 product that's expected, and that has to do with what we would call regioselectivity. Apparently this is the region where the alkene would be favored to form rather than this location. That's called regioselectivity. So why regioselective for that alkene? So that's what we want to discuss. And to discuss that, you want to think about what's called the Zaitsev's rule, which says the more substituted, the more stable an olefin you have. Okay, what does that tell us? Well, let's say we compare all of the C6H12 alkenes. Here's one regioisomer that's possible, or constitutional isomer, same. And here's another constitutional isomer that's possible, but what we are saying here is that this isomer is more stable than that. Why is that? Well, because this olefin, or alkene is another word for olefin, this olefin or alkene is doubly substituted. When we say substitute, it just means the functional group has something other than just hydrogen. This alkene has 3 hydrogens, only one of the 4 is replaced with alkyl group. This olefin has 2 alkyl groups, now which is not as stable as this. Now here you might say both of these are disubstituted, but this is cis, this is trans, meaning the 2 substituents are on the same side of the double bond. Here they're on the opposite side of the double bond. They're further apart, so there's less steric hindrance, and so for that reason this is more steric strain, less steric strain, and it's more stable, and which is not as stable as the tri-substituted olefin. And then of course the ultimate would be tetra-substituted olefin, right? So this would be the most substituted olefin, so most stable, according to the Zaitsev's rule. Okay, so here I hope I didn't confuse you. We were comparing stability, not like energy. Energy would be the other way around. This would be the lowest energy, most stable. Now you might ask why this trend. Remember when we're talking about carry rule, we talked about how more S character carbon, like sp2 or sp carbons, have higher S character. They have higher electronegativity, right? If these carbons are electron hungry, it's better if you can surround them with electron rich atoms like carbons instead of a bunch of hydrogens, right? And so for that reason, the more substituted, the more stable an olefin is. And the key idea here is that the E1 product, at least the major product, will obey the Zaitsev's rule. Okay. And that's why we saw that this is a much more major of a product than this less substituted product. We often call this the Zaitsev product because it's more substituted of a product. Okay. Now, I think during the class time we're gonna tackle this problem to see what we would expect. Sorry for the symbol not showing up. That's supposed to be this delta sign, which means heat, but we'll see you in class for that.